In this video, I'm going to explain how to calculate work from a graph. This will be the second way for calculating work. The first way was from the formula that you did in previous lessons. First of all, I want to review something from Unit 1. So in Unit 1, we could actually calculate displacement from a graph. So we had a formula for velocity. Velocity equals displacement over time. And when you rearrange that, you can get displacement equals velocity times time. Displacement equals velocity times time. And I told you that what you can do to calculate displacement is to actually calculate the area of a velocity versus time graph. Okay, because this is velocity times time, it can be obtained by finding the area of a velocity versus time graph. And that's true, like that setup is true for any kind of equation where you have one quantity equals one variable times a second variable. Okay, to figure out the quantity, you can always find the area of the graph of those two variables. And we're going to apply that concept to the formula for work. Okay, so the formula for work is force times displacement times cosine of theta. Now I'm actually going to ignore the cosine of theta part for now. Let's just imagine that work equals force times displacement. Well, if work equals force times displacement, then using that concept I just said, you should be able to find work by finding the area of a graph if these two variables were the axes. So that's what this picture shows. Work can also be obtained by finding the area on a force versus displacement graph. Okay, the axis has to be force and displacement. Now, this thing I wrote in brackets here, this technique of finding the area only applies when the force and displacement are parallel. Only when the force and displacement are parallel. And that's due to this cosine of theta thing. If you plug in 0 degrees for the angle, cosine of 0 equals to 1. So then work would just equal to force times displacement. So that's why these two have to be parallel, so that I can plug in 0 degrees here, and the formula is just work equals force times displacement. And then I can apply that area concept. Two things to note. One is that if the graph is above the displacement axis, like it's showing right now in this picture, then the area you calculate counts as positive work. And then if the graph is below the displacement axis, then the area that you calculate counts as negative work. Remember, work can be positive, negative, or 0. Sometimes if you calculate the area, you'll have some above and some below, and they might add up to 0. Then you can say that 0 work was done. All right, so just one example here. A 50-kilogram thrill seeker goes bungee jumping. The displacement from the starting position to the lowest point in the jump is 30 meters. The force that the bungee cord applies on the person is shown in the graph below. Determine the work done by the cord on the person. What about the work done by gravity on the person? So I'm just going to focus on the first part where it says determine the work done by the cord on the person. I'll focus on that part first. So how do we calculate the work done by the bungee cord? Well, we have two options. One, we can use the work formula, or two, we can apply what we just learned, which is to calculate the area of the graph. And the graph is right here. Okay, this graph is for the bungee cord. So I first want to explain why the graph looks the way it does. First of all, I've labeled the horizontal axis with displacement in meters down, though I forgot to put the vector arrows in the slideshow. I apologize for that. So horizontal axis is the displacement down. Now, the displacement is 30 meters in total. Okay, it says the person gets to a lowest point 30 meters down. However, the graph doesn't seem to start until 15. Okay, why does it not seem like the graph starts until 15? Well, that's because for a bungee cord, I'll try to show you what happens with the bungee cord. So I've just got my exercise band here. That'll act like the bungee cord. My Coke bottle will act like the person. So at the beginning of a bungee jump, how much force is this cord applying on my Coke bottle right now? Pretty much zero, pretty much nothing. And if the Coke bottle starts to fall down, so it falls down, falls down, falls down, how much force is my cord applying on the Coke bottle now? Well, still hardly anything, because the cord is quite slack. Okay, the cord is not applying hardly any force at all on this Coke bottle. If it falls down a little bit more, it's still pretty slack and not applying any force. Only when it starts to go tight, okay, now the cord has started to go tight. Now it's applying a force on the bottle. And now it's applying a force on the bottle. And for a bungee jumper, the bungee jumper is going to keep going down and it's going to stretch the cord. And the more it stretches the cord, the stronger the force is going to be. And that's why the graph looks the way it does. So for the first 15 meters, basically, the graph is saying that the cord is still slack. The cord has not begun to stretch yet. And now it begins to stretch, and as it stretches more and more, the force gets stronger and stronger and stronger, all the way to negative 1,960 newtons. Okay, now I've labeled the vertical axis force in newtons down. Force, this is the bungee cord, remember? This is the force of the bungee cord in newtons down. But the bungee cord applies a force up on the person, doesn't it? The bungee cord applies a force upwards on the person. So why did I label this down? It's because the two axes have to match in direction. So because I label displacement down, I've got to label force down. Okay, this area of the graph method only works if you've got matching units with matching directions. And that's why I have a negative value for force. Okay, the force is up. So since I labeled the axes down, the value of the force is going to be negative 1,960 newtons down. So negative down is going to make up. So that's a little bit complicated. I made it sound complicated, I guess, but it's not too complicated. Okay, negative down is up. All right. So anyways, now I'll calculate the work done using the graph method. So that just means find the area. So what you do is you go to the end of this line and you then draw a perpendicular or a line straight down to the axis, and then you calculate the area of that. So that makes the shape of a triangle. So the area of a triangle is base times height divided by 2. So what would the numbers be? So the base of this triangle, well, it goes from 15 to 30. So how far is it from 15 to 30? You subtract the two numbers and you get a base of 15 meters. The height of this triangle, well, it goes from 0 down to negative 1,960. So the height of this triangle would be negative 1,960 newtons. So you fill those in, base times height divided by 2, to get the area of a triangle. get in the calculator, and I come up with negative 14,700. And the units of work are joules. And there's no direction in my answer because work is a scalar. Work is a scalar, not a vector. All right, the other part of the question asks you, what about the work done by gravity on the person? What about the work done by gravity on the person? Okay, so there's two methods to calculate work. Either you use the work formula or you use the area of a graph method. Well, we're not given the graph of gravity. This was the graph for the bungee cord. We're not given the graph for gravity. So we have to just use the formula for work to get the work done by gravity. The formula for work is the magnitude of the force times the magnitude of the displacement times cosine of the angle between them. For my first step, since I know the formula for the force of gravity is mg, my first step is simply going to replace the force with mg. Now I'm going to fill in the numbers. For mass, it's given in the question, 50 kilograms. For g, the gravitational field strength, that's 9.8 newtons per kilogram. The displacement is 30 meters. 30 meters. Gravity acts on the person for the entire 30 meters. So we put 30 in there. Cosine of theta. So theta is the angle between the force direction and the displacement direction. However, they're the same direction. The force of gravity is straight down, and the displacement of the bungee jumper is straight down. Okay, they're straight down. They're in the same direction, so the angle we use when they're in the exact same direction is 0 degrees. There is no angle between them. So I plug in all those numbers. Cosine of 0 degrees equals to 1. So that's not going to affect anything. So the answer is going to be 50 times 9.8 times 30, which turns out to be 14,700 joules. Okay, so there was a mistake there. This turned into 180 somehow. I'm going to fix that for your slideshow, for your notes. But anyway, the answer is 14,700 joules is the work done by gravity. And you may notice that's the same number we got for the work done by the bungee cord. One of them's negative, one of them's positive. And you may be wondering, is that always going to happen? And the answer is no, definitely not. It will happen in very special situations. This is one of the special situations, but we will talk about that in a future lesson. Okay, we're actually not even close to talking about that yet, so just got to be patient with that. So what you'll do is a few practice questions. Some of them will require you to calculate work with area. Some of them will require you to use the formula. Some of you will require both. And then you can submit it if you want to get feedback, but it's not mandatory to submit it. All right, see you next time.